All right, folks, I want to do one more optimization example for you, and then I'm going to turn it over to you to work on these on your own. Now, I'm going to be putting out some, like a document with some exercises, some optimization exercises, kind of like I did for related rates, and then I'll make some separate videos where I go over the solutions to those exercises. Okay, so the example I want to show you is another real-world example from business. So this deals with price and demand, like basically demand being like the sort of relationship between the price you sell an item for and the number of items you produce and attempt to sell. So it's going to be about that, and then also about revenue, which is the total amount of money you get from the sale of all the items. There's a few underlying assumptions we're going to make that you usually make when you're studying business applications like this. And that the first assumption is we're going to aim to, as a business, we're going to aim to produce exactly the number of items that we can sell. And we're going to aim to sell all of the items we produce. So the number of items, which is going to be represented by the variable x in this problem, the number of items we sell and the number of items we produce is the same. That's x. Now, in order for us to sell all of the items we produce, we have to set the price at a value which is going to be, which will cause enough people to want to buy it, to be willing to buy it, according to the amount of demand for this item. So that means if we're only going to produce and sell a small number of items, we can sell it at a high price. But if we want to produce and sell a large number of items, we have to sell it at a low price. And the price is given as a function of the number of items by this, according to this function here. So let me just draw a little picture of that function. If you remember back to when we studied exponential functions in like college algebra, then you may be able to figure out what the graph of this is going to look like. It's going to have a y-intercept of 12 because 12 is the constant multiple of this exponential function, and then given that the relative rate here is negative, that negative 0.1, that means we're going to have exponential decay. So let's just draw what that looks like. We'll have, this is price versus quantity x. It's going to have an intercept of 12 over here, and then it's going to decay like that. It's going to decay exponentially like that, according to this function, p equals 12 e to the negative 0.1 x. Now, some demand functions, this is called a demand function. It relates the quantity and the price. But some demand functions are linear, so they cross over the x-axis, and that gives you kind of like a maximum quantity of items. But this demand function is exponential. It still goes down, it's still decreasing, which all demand functions are decreasing, because as you increase the number of items, you have to decrease the price in order to get enough people to buy it, right? So they're always decreasing, but this one is decreasing exponentially, which means x can be as big as you want. So the domain for this, we're going to go ahead and set up the domain right away, is anything from 0 items to as many items as you want. Okay, having an exponentially decaying demand function allows you to kind of consider, well, what if we want to sell thousands of these items? We just have to make the price really small, and then everybody's going to want it, right? So that's not necessarily a safe assumption, but that's the way we're going to do it in this problem. So now, the question is, how many items should we sell to maximize the total revenue? Total revenue. Well, okay. What is revenue? Revenue is the total, the total amount of money you're going to get from the sale of all the items. So every time you sell an item, the amount of money you get is equal to its price, right? The price you sell it for. So P is the money you get for selling a single item. How many items are you selling? X. So if you sell X items for P dollars each, your revenue is going to be X times P, right? Number of items times the price per item is the total amount of money. Now we're not talking about profit because we have no cost function involved here, so we'd have to take the revenue minus the cost if we wanted to get profit, just by the way. But in this problem, we're going to deal with revenue is items times price per item. So okay, let's start going through our process. In step one of the process I've suggested, I say draw a diagram. It's not really a diagram to draw here. I mean, I did draw this function, I guess, but the main thing I want to do here is just establish what all the variables are. We've got the number of items, X. We've got the price per item, which is P. And we've got the revenue, total, which for that I'm going to use R. Okay, so moving down here, step 2. The primary equation for this, the primary equation should be it should give me the revenue, right? So the primary equation is, what is revenue? For that, I'm going to use what I described here. Revenue is X times P. Okay, R equals X times P is my primary equation. So then, step 3 would be the constraint, the secondary equation. The constraint is the demand function. The constraint is how is the price related to the number of items. So that's P equals 12 e to the negative 0.1x. So now in step 4, we're going to substitute that in. We're going to take the 12 e to the negative 0.1x and stick it in for P in the revenue function, in the revenue equation there, and get revenue as a function of items. Revenue is a function of how many items you produce and sell. Will be, I'm going to put the 12 out front because I like to put constants in front, and then I'm going to put the x, and then I'm going to put the e to the power negative 0.1x. And that is our function. Now the domain in step 5, I'll put a little 5 over here. Domain we already figured out. That's going to be 0 to infinity. So that means that we're not going to be able to do the closed interval method. So that means we're going to have to use either the first or second derivative test. But either way, I've got to find my critical numbers, right? So for critical numbers, let's get the derivative of this revenue function. This is derivative with respect to x, and it's a product right here, right? 12x times e to the negative 0.1x. So I need to use the product rule. I'm going to have the derivative of 12x is 12, and then multiply by the second function. And then plus 12x times the derivative of e to the negative 0.1x, which would be e to the negative 0.1x, and then times the derivative of negative 0.1x, which is going to be just the negative 0.1. So there's my product rule, giving me the derivative of r. If I simplify that slightly, I can factor out a 12, and I can also factor out this e to the negative 0.1x. And then from the first term, I've factored out everything, which leaves me with 1 left over. And then in the second term, I've factored out the 12 and the e function, and then I'll just have the x left over and this negative 0.1. So since I'm adding, but it's negative, I'm going to write minus 0.1 times the x. So there we go. All right. Factor that out. Now I have this. So now in not step 7 yet. I haven't found my critical numbers. Slow down, Tristan. All right. So is this ever undefined? Well, since we're using this, exponential decay here, that's never undefined. So no, it's never undefined. R prime, never undefined. When is R prime equal to 0? Well, if you set this equal to 0, we've done problems very much like this before. When you have like this exponential factor that you factor out like that, that exponential function is never equal to 0. I mean, look at the picture, right? This is the exponential function. It never crosses the x-axis, right? Powers of a positive number will never give you 0. So that part can never equal 0. The only thing that can happen is that this equals 0. So 1 minus 0.1x equals 0. Solve that for x, and you get x equals 10. Okay, so that's our critical number. We only have 1 again in this problem. Similar to a previous problem, we only had 1. There was actually, I guess in example 2, we had 2 critical numbers. In example 1, we only had 1 critical number. And here again, we only have 1 critical number. But the question remains, is that critical number giving us a maximum or a minimum? Hopefully it's giving us a maximum, right? Because that's what we're looking for. Our goal as a business is to maximize the total revenue. So to figure this one out, I think in a previous example I did the second derivative test. For this one, let's do the first derivative test, just to mix it up a little bit. And also because I guess this derivative is a little bit annoying to take another derivative of. It's easier to just sort of evaluate it at some numbers. So our domain, remember, is 0 to infinity. So let's first of all, plot our number line with 0 as a boundary. Critical number is 10, so that's an important number here. That divides us into two intervals, that one and that one. So I'm going to pick the numbers 1 and 100. And I like powers of 10 here, 1 and 100, because I'm doing 0.1 times x in here and in here. And so 0.1 times x is going to be easier to work with if x is also already a power of 10. So now all I need to do is check RPrime. This is a power. Remember, this is a sign chart for RPrime. We want to know if the derivative is positive or negative, so we know if our revenue is increasing or decreasing. And so I need to put 1 back into this function, our RPrime function here. You can be guaranteed that 12e to the power negative 0.1x is going to be a positive value, right? Because again, that's always positive. It never goes beneath the x-axis. So all we have to look at is this factor, 1 minus 0.1x. And if x is 1, 1 minus 0.1 is like 0.9. That's a positive number. So there we go. Positive on that entire interval. Then if you plug in 100, 1 minus 100 times 0.1, this is going to be like 1 minus 10. This is negative 9. Negative, and therefore negative on that entire interval. Since the first derivative is changing from positive to negative, it's increasing to decreasing. And now we can conclude that revenue is maximized when x equals 10 units. So you should only produce 10 units and sell 10 units at whatever price is given by 12e to the power negative 0.1 times 10. Calculate that out. I'm actually curious. What is the price we should sell these units for? 12 times e to the power negative 0.1 times 10, which is like just negative 1. I guess that's 12 over e. $4.41. So produce 10 things and sell them all for $4.41. And then hypothetically, that should maximize your revenue if our demand function is correct. So that's the end of the optimization problem. I think I just said at the end there, if the demand function is incorrect, it is interesting. It is interesting to ask where does that demand function come from? Like where the heck would you actually get that function from if you were a real business? I mean, I don't know a lot about business, but my impression is that you'd get that information from market research, right? Like you would do a survey, poll some people, or look at actual like purchasing trends for similar items on the internet. Maybe like check out some Amazon data or something. I don't know if Amazon makes their like purchasing data like available to businesses, but if they did, that would be pretty sweet. Because you could just look and see like what like for different possible prices of similar items, how many people are buying, right? And if you either poll people or look at the data, you should be able to do some sort of data analysis. Maybe do some curve fitting with like linear regression or exponential regression, and then figure out what that function would be to describe the relationship between how much you sell the item for and how many people are willing to buy it. So there you go. So that is optimization applied to business.